Hi everybody, welcome to our next topic in study of light and specifically the wave properties of light. What we want to look at today is kind of an extension of where we've been looking at with diffraction and interference. And we want to look at something called diffraction gratings today. Diffraction gratings are these pretty cool things. Um, and what they really are is they're kind of like the double slit, but they're taken to the extreme. So really, they're like a bunch of slits side by side. So a diffraction grating is a surface that has many close, equally spaced parallel lines, and so each of these lines is going to act like a source of light. So they're going to be very, very close together. You can have hundreds or thousands per centimeter, and so they're very close together, and each one of these is going to act like a point of light. And so it's like a double slit, but we can, instead of having two, we have, hundreds or thousands of slits. Um, and so each one of these acts like a source, and then we can actually then observe interference and diffraction from each one of these. And we see some pretty cool patterns from these things. Just so you know, we can have two different kinds. We can have a transmission grating, which means the light goes through it, or we can have what's called a reflection grating, where the light bounces off of it. And we'll take a look at some examples of both of these in just a few minutes here. But let's take a look quickly at just a simple example of a transmission grating. And so that's kind of what this diagram is down here. And so in this transmission grating, you've got incoming light here. So the red lines here is the incoming light. They're going to go through different numbers of slits. So in this case, there's 5 in this diagram. And each slit is separated by some distance d. And then the light is going to, of course, go off in all directions. But let's take a look at the light that's going off at this angle theta. And the light that's going off at this angle theta is, of course, going to meet at some other fairy distance point here. And again, we're going to be looking at large distances compared to the scale here. So we're going to consider these lines right now to be parallel. So they're all heading off in the same direction. And so we can say then that the path difference for this ray compared to this ray is just delta L. So what that means is then each ray is kind of out of step, or a path difference of just d sine theta. So it's out of step from its neighbor by that distance there. And so what's kind of neat is that we can actually recycle most of the work we did for our double slit experiments and just use it again for our the diffraction grating, because the same sort of principles apply. We still have the waves that are out of step from their neighbor by the same sort of amount, because it's the same sort of analysis we're going to be doing. And so that we're actually going to have the same sort of equation, that the the mth order, so like the first, second, third, 0th order bright fringe, is going to occur at this angle theta m, and it's going to be given by this expression, which again should look pretty familiar. This should be the exact same expression that we had for the double slit. And so this is again our diffraction grating example, which is great again because it's the same as what we had before. So awesome. So then probably the question we can ask ourselves is, okay, well, if it's the same sort of pattern we're getting from a double slit, why on earth would we want to use a diffraction grating? Well, that's a great question. I have 3 kind of answers for you for that one. And so yeah, why use the grating then instead of just 2 slits? And my first answer is that because we're having more slits, we're actually letting more light in. So instead of having just 2 sources of light, we're having, tens, hundreds, thousands of sources of light. So we're actually going to have a brighter pattern. So it's going to be easier to see these things. So we can actually see lots of these things a lot easier. Another really good reason is that if we're having a bunch of these slits, that it's quite easy to get them much closer together now. So if we're going to bring our slits closer together, hopefully remember that means that our diffraction pattern will be further spaced apart. So it's going to be easier to see successive maxima because they'll be further separated apart. So we don't have to be nearly as far away from our source in order to see or distinguish these different bright spots. But the other really cool thing about a diffraction pattern, and the main reason why I think it's pretty neat, is that the maxima are sharper and more defined. And so I think what's kind of neat is if you take a look at how does the pattern change as you add more slits that are involved. And so if you have the double slit, you see the sort of pattern we looked at the other day. You see this sort of maxima here, minima here, but it's this blend. But as you add more and more slits, the maximums become much more sharper, much more defined. So it doesn't really make it more, it doesn't move them at all. They're still in the same location, but it makes them more distinct from the neighbor. So really, really sharp maximum here with 100 slits, and then in between, very, very dark. but just again to show you that it doesn't actually change where the maximums are, but it does change kind of the neighborhood around it. So right in the middle before we had a minimum, and we still do here, from 2 slits to 100 slits, but it's not this gradual drop off like it was with 2 slits. It's on, off. And so that makes it a lot easier to spot these things. And so this is one of the reasons why, again, diffraction gratings can be far superior for a lot of things that just a double slit can be. All right, so let's do a quick example here. So a diffraction grating has 5,000 lines per centimeter, and we're going to illuminate it with blue light. And there's the wavelength of blue light. And I want to know what angle will I see the third order maximum. So again, we're dealing with a diffraction grating, so hopefully we know which kind of expression we want to use. It's this one. So here's the expression we want to use here. So here's our expression for the diffraction grating. And we want to deal with the third order maximum, and we have how close the lines are, sort of, and we have the wavelength. So we have to do a little bit of work here because we don't directly have all the values we need. Let's list what we do have. So we know a couple things. We know that we have our M, oops, try that again here. We know what we have. We have our M is going to be 3 because it's our third order maximum. We know we're looking for our theta 3. What is our third order maximum? We have our wavelength. It's 450 nanometers, or 450 times 10 to the minus 9 meters. And we need to know what D is. So if you remember from our first page, D is actually, again, the separation of the slits, or how many meters are between the slits. And we don't have that directly. We have how many lines there are per centimeter. But if we know how many lines there are per centimeter, in order to get how many centimeters there are in between each line, I just have to do the inverse of that. So 1 divided by 5,000 lines per centimeter. And so if I punch it in my calculator is going to spit out 1 over 5,000 is 2 by 10 to the minus 4. But notice this is going to be in centimeters because I'm doing lines per centimeter. So now it'll be in centimeters per line, but I can drop the per line. So this tells me again how many centimeters per line, but I want it, of course, in meters. So then I just write it as 2 by 10 to the power of minus 6 meters. So now I'm ready to use my expression because I've got everything I need. I'm looking for theta 3, and again, I can trust that you can plug this into a calculator and get an answer. Hopefully I did it correctly as well. I'm getting as my angle here 42.5 degrees. So you can see that's a lot bigger separation than we were getting with our double slit experiment. And the reason being, again, because the slits can be a lot closer with a double slit experiment. Or sorry, with a diffraction grating, because we get so many more packed closer together rather than just 2. And so it's a lot easier to see things that are 42 degrees away from each other than like 0.2 degrees away from each other. So that's a nice thing we can do. All right, so there's a numerical example. Let's do a quick conceptual question here. So let's pretend we're using the exact same grating. Well, maybe not as the last question, but we were using one grating, and we have two different light sources. We have a red light source, and we have a green light source. And if I shine those both on the same screen, the same distance, everything else is the same, besides the color of the light, which one will have a bigger separation in the maxima? What that means is which one will have the interference pattern more spread out. So again, as we usually do, I want you to think about this, pause the video for a minute, and when you think you've got an answer, start it up again. So again, looking for which one of these, red or green, will have their lines further apart, and I want you to tell me why. So when you're ready, start the video again. Okay, so hopefully you've got an answer for me. And so let's just maybe jump to, well, let's go to the explanation first again. So what is causing the separation here? What would cause one separation more than another? Well, it has to do with the wavelength. So which one has a bigger wavelength? So red has um, a longer wavelength than green does. So red has a bigger wavelength. So I'm going to write big over red. maybe I shouldn't be using a red pen. Actually, let's switch to green then. So big for red and little for green in terms of the wavelength. And if we look at the expression, let me steal it from the last page. If we look at that expression there, um, the wavelength is here. So if we have a bigger wavelength, we're going to have a bigger theta m. So what that means is bigger wavelength, bigger theta m, which means bigger theta. So it means the red light will have a bigger theta. So what that means is for the same maximum, the same separation of slits, the same everything else, that red will have a bigger angle. So what that means is the red light will be further spaced out. And so what I've got for you is a nice little picture to kind of sum that up. So here's actually what you would see if we did this experiment, and we can maybe try and do this in class. I think I've got different color lasers. We'll give that a try anyways. So you'd see the central maximum, nice and bright, and then you'd see the first order maximums for the red there, but the green is only right there and there. And again, in a schematic one, you can see it here. So the central and then further off to the side, but the red is always further away. Okay, so hopefully you got that. Now let's just take a quick look at some neat ideas here. So we talked a lot about transmission gratings here, but we have kind of ignored reflection gratings. But luckily, don't worry, the analysis is exactly the same. But one of the neat things is that you probably have reflection gratings. They're certainly falling out of use now, but CDs, DVDs, HD DVDs, or Blu-ray DVDs, those sorts of things, they're actually can serve as reflection gratings because really what they are is a bunch of tracks, and the tracks are made of these different pits and valleys and things like that. And so each one of these acts as like a different line in a diffraction grating. And so if you've ever noticed that a CD has kind of like a rainbow pattern to it when you look at it, it's because of this diffraction pattern. It's actually breaking up the light into the different colors based on the angle you're looking at it. So let me go back to this one for a second. If you have white light coming in here, hopefully you can see from this little example that it's going to spread out the colors, right? So some colors will go here, some colors will go here, some colors will go here. And if you're looking at one spot, you're going to see different colors. And so that's kind of what a DVD does. So we can actually use a DVD as a diffraction grating as well. And so that's kind of neat. And so one of the questions we're going to have for you in the kind of survey at the end here, DVDs store more data than CDs do. So what that means in terms of their tracks, DVD tracks are closer together than CD tracks are. So if I took a DVD and a CD, which one do you think would have more of a rainbowy appearance, a DVD or a CD? So think about that one. I'm going to ask for your answer on that survey question. So that's that one there. But I think, again, that's something kind of close to home that you've probably noticed, and now you can kind of explain it and impress your family about how smart you are and how cool physics is, because we all know it's awesome. And the last thing, again, that's I think is pretty neat, something that scientists use for all sorts of different things. And again, if you continue on in science, you'll see why knowing the wavelength of light is often super important, but something called the spectroscope. So we take light coming in of some unknown wavelength here, you pass it through a grating, and you can swing this, they call it a telescope, but this sort of eyepiece through some known angle. So you measure theta, and whenever you see the bright spot, you actually then, by measuring that angle, can know exactly what wavelength this is. So you get this to an actually pretty close order of magnitude, or pretty close order of precision, what wavelength this light is. And so again, if you've ever done sort of stuff with spectroscopy and chemistry, or talked about the color and spectrum of stars, this is exactly what sort of stuff is going on. This sort of basic idea, breaking up light with a diffraction grating and seeing where it is. So I think that's some pretty cool stuff. Hopefully the math wasn't too heavy, because again, we've done a lot of the heavy lifting already. If you have any questions, let me know. But that's going to be it out of me for today. Have a good night, everybody. See you tomorrow.